Hi friends, today I am going to discuss something new like the mathematics topics. It's a limits and I will describe with the algorithms, and let's see here what is the limits. And first I will describe it theoretically and then I will apply like a as a algorithms with the Python language. So see here, let's see the open like a Google Colab. It's a it's a Google Colab here. Okay, so first I need to open here Google Colab. So first we need to remove something. Wait 1 minute. So should be like a Google Colab visuals. Yeah. And previous class we have already discussed so many things. So I hope I will continue from there. So if you didn't see my previous video, so you must watch. So your concept should be clear if we are going away from here. So that I have already discussed how to write expressions, how to write variables, and write linear equations, and how to draw like this symbols graph like a linear equations, quadratic graphs like a quadratic equations, and I have already discussed exponential form, and we can also plot like this. And summations we did discuss summations of elements in the Python's exponentials also I have already discussed, and Euler also I have discussed here, and limits did I discuss something like the basics, and derivatives did I discuss like this. So I have already discussed the derivative till discuss derivatives. So if you are it's a friendly of this, so let's first I try to run, so run all, and then I will start from itself. So it's all on, it will take a time, so don't worry. So it's a limit, it takes time, don't worry. Yeah, you can put any number because this is the algorithm it's running. It's a So let's see the limits, just Euler numbers and some interesting ideas like emerged when we forever increase or decrease the input variable, and the output variable keep approaching value but never reaching it. So I have discussed. So let's watch in my previous video. So limits means if I write like this, so if I write here, let's see like a limit x tends to infinity. So x tends to infinity and 1 by x, so it should be a 0. So the way as I read x approaches infinity, the functions 1 by x approach 0 but never reaches 0. So we will see this kind of approach but never touch behavior a lot. So especially when we dive into a derivative and integrals. So we have already explained, so how do we write like a in the like a SymPy. So we did use a SymPy, and we have discussed this value, how to get a output with the algorithms like a Python language. So first we have discussed like a from SymPy import and star here, because I am importing the all module in SymPy, and x should be equal to the like symbols, and we represent like a x as a syntax way. And now your next variable should be like a 1 by x, it's a functions like this, and now result should be equal to limit, and you write the variable like a functions, and x and infinity you can put twice zeros. Now print result, it's a print and result, it's a result. So you have gotten like a output, which should be, let's see here how to get a output. So let's go here, and you will see here it's the limit I have written there, it's a this is a way, and I have gotten here output. And another, just I have already written one more, it's a value, it's a derivative steps, and it's a natural log, and it's a limits. Look here. So this is a way we can write our output. So let's write this something, it's one more thing, let's see here, just we are discussing here the limit, it's a limit, and now from SymPy import and put here a star. Now we will create the one functions, x should be equal to symbols like x, and f should be equal to f will equal to 1 divided by x, result will equal to limit, and write a function like a f should be x, and put double zeros, and what will be the output here? So let's the print and result, it's a result. So did I get some mistake here? It's a functions f, it's a x, so should we write here the comma here, should be right here like this. Now it's solid. So let's see, I have gotten the output here 0. It's a basic rule, so I hope it's a you can understand these limits. And another I have already discussed, this is a way we can put the infinite number of values. So it's the power of the SymPy. And next after that, in the derivatives means let's to talking about like a functions and look at them some calculus perspective. So starting with the derivative. So what is the derivative? It tells the slope of functions, and it is useful to the measure the rate of change of any point in a functions. So let's see why do we learn like a derivatives. So let's we used if we are often used in a machine learning and other mathematical algorithms, especially with the gradient descent. So when the slope 0, that means we are at a minimum or maximum of an output variable. So don't worry, we will discuss the linear regressions, logistic regressions and neural networks in the it's a next topics. But if I write here like a functions like a fx will equal to x square, so how steep is curve at x will equal to t, 2 and 3, 4, 5 and etc. So if we take like a x will equal to 2 and nearby value it's like x will equal to 2.1, and when the passed to the function fx will equal to x square, so what should we write here? So we should write something like this. So let's see here. So first we need to the erase here. It's a eraser. It's not the eraser. I think it's what is this? Yeah. So it's a derivative look like. So suppose we have a functions like a fx will equal to x square. It's a, so here we will describe like the how steep is the curve at like a x will equal to some specific value like a x will equal to 2. So we can measure steepness at the any point in the curve, and we can visualize this with a tangent line. So think a tangent line as a straight line that just touches so the curve at a given point. It also provides a slope at a given point. So we can we can estimate a tangent line at the given x value by creating a line intersecting that x value and radially close neighbor x value on the function. So if I write here like it's let's say x should be 2, so what happened, and near value like it's a near value should be, it's a value like x should be 2.1, and now I am putting, so what will be the if f2 we can write here, it should be the 4, and if you can put here 2.1, it should be 4.41. So resulting the passage and these 2 points like it has a slope 4.1. So let's see the how do this. So it's look like we will observe look like a curve. So one of the identity just if we have a 2 point like look here, one is the straight line here as a point and another is a b. So if I want to get here the slope of this, so we can say the m as a slope, and it's a x1 y1, and now we can put here x2 and y2, it's a coordinate part here. So how to get the slope? So we can write like a y2 minus y1, it should be divided by x2 minus x1, and we can easily get here like a value of, so let's according to this it's a y2, it's a y, so what will be the x1? So if we take here the x1, like a 2, because we are assuming x will equal to 2, so we have gotten a y1, it's a 4. And similarly, according to here, it's a 2.1 we are assuming, so we have gotten 4.41. It's a, now how do you get the, what will be the slope? It should be like a 4.41 minus, it's a 4, and it will be divided by 2.1 minus, it's a 2. So what happened? So let's see, dividing 0.41, and it's a like a 0.10 should be divided, so it's look like a 4.1. This will be the slope. So if I made the x steps between the 2 points even smaller, like x will equal to 2 and x will equal to 2.00 something, so when we result like a 4 and another f 2.00 something, it's a 4.00 something, so that would get a really close to the actual slope, like a 4 value at the given point in a curve. So let's see, so we can apply the so many applications, so don't worry. And so let's derive these steps and try to understand with the algorithms. Let's see here. So in the derivatives, so let's say I am going to the defined derivatives underscore x, and we have written here like a, it's a f x and stepwise, because stepwise, and m will equal to f x plus stepwise and minus f x divided by the x plus step size, it's not a y, it's just size, and minus x, and return m, and we are getting a like a slope. And define underscore my functions x return x square, slope underscore at 2 will equal to derivatives underscore x my underscore functions 2 and 0.001, it's a print, right? And we have gotten the output just few minutes back, we have gotten it's the same value. So this is a way, now it's a good there is a clear way to the calculate the slope with the algorithms, and we have already discussed with the pythons. Similarly, we can take the another functions and we can use and do a more practice. So let's calculating derivatives, and so calculating a derivative in a SymPy like this. So let's from SymPy import just I have already discussed here, and x should be equal to symbols and it should be write x, and now it's a declare x to SymPy, and now the just use a Python syntax to declare a function. So what is your function? So now I am writing the function f should be equal to x, and it's like a 2, and now calculate the derivative of the functions. So we will create like a df underscore functions, it should be equal to di double f, and it's a functions like x, and print here, it's a print df underscore, it's a f. Let's check it. Yeah, just I have gotten, it's a output like a 2 to the power x. So by declaring a variable using a symbols functions in SymPy and we can proceed to use a normal Python syntax to declare my functions. So after that, we can use a diff diff to calculate the derivative function, and we can take our derivative functions and to plain Python and simply declare it's the another functions. So derivative calculators in a Python. So similarly, if we want to write here like a derivative calculator in the Python, so let's see. Derivative calculator. It's in Python. It's a diff, and we are going to create as a functions. So it's a f and now x. Return x and just discuss here x square, and if we want to the diff dx underscore f, it's a x return it's a x, and now we get a slope. Okay, it's a diff. Should we go back? It's a slope at the rate of like a at let's go 2 should be equal to dx underscore f 2.0. So put here 2.0 and print slope underscore at underscore 2. It's a we have gotten here 4 test output. So if you want to, if we want to keep using a SymPy, so we can call like a sub functions and functions to swap the x variable with the value 2. Similarly, calculate like a slope at x will equal to 2. So we want to calculate like a, so we can do one more. Otherwise we can also write this. So print df underscore f functions dot subs and x and 2 here. It's a sub functions. So just let's see, we have gotten like this. So I hope it's a clear till here. Now after that we need to the another concept. We are going to discuss the another concept, and we will encounter like a, it's called a partial derivative. It's not a difficult, but we will try to understand here. So these are the like a derivatives of the functions. We have a multiple input variables. It's So let's see here, just we are it's the slope on a one dimensional functions. We have a slope with respect to the multiple variables in a several directions. So for each given variable derivatives, we assume the other variables are held constant. So let's take the suppose we are taking the 3D graph, and just if I discuss like a 3D graph, so let's go here. So 1 minute, it's now I am going to the erase these things. It's called a partial derivatives. It's a partial derivatives. So partial derivatives. So if we are taking this, it's a one functions x comma y, which way 2x cube plus 3y cube, and we will see we have a slope of the two directions for the two variable, and we will see here. So this is the functions, and one is the x cube, another is the y cube. So the x and y variable each gets own derivative. So it's a x and y variable, so y variable each get. Similarly s and t, when we others can take here, it get their own like a derivative, like the one you can write the dy dx, and another we can write here dy dy. So these represents the slope values with respect to each variables, and on a multi-dimensional surface. But and this is also called like a technical way, like it's a slope gradients when dealing with the multiple dimensions, and these are the derivatives x and y. So let's see, according to the SymPy, how do we calculate in the SymPy? So first let's do the answer. So let's see here. Just I am going to the first partial derivative. So if I write here like this, is here dy, it's a dx, so 2x cube, it's a 2x cube, and we can write second value as it is same, so 3y cube. So it's a constant, so we are assuming this one is the constant, so your answer should be like only the 3 times 2, it becomes 6x square. And the another, if I am differentiating with respect to the dy, then your first value should be the like a constant, and it should be like a constant, and another like a, so you can write like a 2x cube and plus here 3y cube, so your answer should be like a 9y square. So how we calculate the partial derivatives to x and y with respect to the SymPy? So your answers like this according to the partial derivatives. So if you want to understand the more details in the partial derivative, you can watch my another video in the full partial derivatives, don't worry. And let's see, I will try to give a link, don't worry. It's a so I am going to start the something we want to the plot here, the 3D. It's a 3D figure. So from we need to the import one more SymPy library, like a from, it's a like a from SymPy dot plotting. It's a dot plotting SymPy dot plotting import plot 3D plot import plot. It's a 3D. Now the declare x and y to a SymPy, and let's declare here it's a one variable like a x comma y. We are assuming like a two both the variable and symbols x comma y. Now just use the Python syntax to declare function. So f should be equal to x three and you can calculate here like a dx underscore f should be equal to, it's a functions of f comma it's a x. So let's see here. Now I want to go, and here we can see here df underscore y, df underscore y, it's a df underscore f should be equal to def f comma y. And after that I want to the print something like a print dx underscore f, and let's see what happens. So it's has been printed. And similarly, if I want to the print the another variable like a print, it's a df functions dy functions dy underscore f. So you can see here like the another. And now I want to the plot these functions. Okay, so I have gotten the some problem. It's a df and it's a dy. So it's a y, I am getting a df itself functions. Okay, and dff it should be like a, it should be okay, put here dy here. It's a, now it's all right. Yeah, it's all right. So I have given these functions, and now I want to the plot here. So let's the plot the 3D functions. So it's a plot 3D, and it's a functions like this. I have, we can see here how to plot like a 3D. So it's alright. I think it's a clear how to plot a partial differentiations. It's a good way to understand this. So next video I will try. So here we have taken like the for the x and y value. So if you take the 1 and 2, so the slope with the respect to the like x is the 1, so 6 into 1 it becomes the 6, and slope will be the respect of the y is 9 into 2 square, it become the 36. So and similarly we can also use like a limits. So using a limits the calculator slopes is the other way. So I will try to in the next video to describe this one, and it's a more differentiations, it's a complex differentiations I will try, and then I will discuss in the integrations. So I hope till here it's to understand, it's a very basic, so let's try to understand. So in next time I will discuss more things. So it's a thank you very much. I am Manibhushan. Thank you.